So thank you for the opportunity. I'll be following on from Mr. Schneider's excellent presentation on the lift controller and how the lift controller is setting up the system and controls the drive from the sort of the other side of the coin, how the drive unit behaves and what are the considerations of the drive in a lift system. My name is Patrik Masson. I'm a global product manager at Nidec Control Techniques. Just a very brief overview. So Control Techniques is actually UK-based, and we specialize on making variable speed drives. We have a global presence, but most of our activities are in Europe. And while most of what we do is actually to do with manufacturing automation, the same sort of technologies have been used successfully in the elevator industry as well. And the elevator industry is a big part of our overall portfolio and what we do. And over the years and over the generation of products, we have implemented a lot of things and a lot of specific functions in our products that have been special and specific to the elevator industry. We started with CiA 417 with our previous generation of products more than a decade ago. And also we've been implementing CiA 417 in our current generation of elevator drives. Just starting from the very basics of what is basically a car drive unit or variable speed drive or drive for just short, starting from a very high level. Basically, the drive is a fairly simple electrical device and what it does is it turns alternating current into direct current and then back into alternating current. So if you have a line input at a typical voltage of, let's say, somewhere between 380 or 480 or even 200 to 240 volts at a typical European frequency of 50 hertz, that gets turned into direct current by the drive's rectifier stage. And then there we basically have full control over the voltage and the current. And then once that's turned back via the inverter stage into the three-phase alternating current, we have full control over the output current, the voltage, and the frequency, and can change these to whatever is needed by the application, and also in line with the motor characteristics that the drive is controlling. So why is this relevant and why is this important in lift applications? Well, an electronic control system using a drive can give optimum motor control, and that's regardless of the traffic requirements or the installation preference, if it's all sized well and tuned well. The high speed and smooth control that the drive can provide basically provides a seamless, low noise and jerk-free ride for passengers of the lift. The accurate and smooth electronic control of the mechanical movements of the system results in less wear of the moving parts. So ultimately that means less maintenance. Emergency rescue procedures can be programmed into the drive itself so that the drive and the lift controller, for example, can work in unison in emergency rescue situations. And that can make the rescue safe and more efficient for the passengers in emergency scenarios. Now, physically, the drive is typically located within the lift control cabinet in the machine room next to the lift controller, but also it may be placed mounted directly in the shaft or next to a door for the more modern machine room-less installations that have been quite popular in recent times. And also an important bit is that the drive and motor together can be very energy efficient, especially if an active front end or a regenerative drive is used. So a lot of that braking energy, a lot of that energy that comes back into the system or is generated by the system, instead of breaking it and burning that energy away as heat with an efficient regen system on the drive, that can be pushed back into the grid or reused by the system, and saving energy overall and making the whole system more energy efficient. Talking a bit about control modes and interfacing. So drives in general are designed to be controller, motor, and feedback device agnostic. We spend a lot of time in trying to work with as many controller manufacturers, as many motors, as many encoder types and resolvers as possible. And also, as it was said before me, basically when all of these devices turn up on site, it's crucial that, for example, the drive can work as quickly and easily and as seamlessly with the controller, with the motor, with an encoder interface as possible, basically saving time and saving energy on the technician's part who's responsible for setting up a lift system on site. Now, industry standard communication protocols play a crucial role in allowing this wide and flexible interoperability. So while there might be different control methods, starting from analog speed reference, where basically a controller gives constant speed commands to the drive, and the drive is really just acting as sort of an amplifier and just delivering the necessary speed and torque on the motor, but the controller is fully in charge, to then moving on to digital preset speed, where there are multiple preset speeds set up in the drive, and the controller is just choosing between speed 1, speed 2, down to creep speed, and then obviously 0 speed. But there's more control and more profiling basically done on the part of the drive. So the drive is no longer just a dumb device, but the drive and controller work in unison in delivering that optimum travel. And then coming on to the different protocols. So some of this can be realized through Modbus, CANopen, and obviously through CANopen Lift or CiA 417, which is just a very elegant and standard way of achieving all this. Now, it's important to highlight in this whole presentation and this whole scenario that ultimately the drive will always be a slave of the lift controller. So in this relationship, the lift controller is the master, is the one that ultimately decides how the lift will operate, and the drive, the slave, will follow and deliver that travel, deliver that movement to the motor in the system. But there are many ways that the drive can contribute to this relationship and make the overall performance of the lift better, as well as take on certain responsibilities that traditionally may have been implemented by the lift controller. Now, in the whole topology, there exists the controller, there exists the drive, and the CAN bus connection between them. The lift controller communicates with the CANopen interface of the drive via the CAN bus, and then these messages received through the CANopen interface of the drive are then passed on to the CiA 417 implementation within the drive. The CiA 417 implementation processes incoming messages from the lift controller and then implements the CiA 417 profile by setting and changing the relevant drive parameters within the drive. The drive parameters are used by the drive to implement the requested travel. So there exist internal drive lift functions that are specific to the operation of the lift, and these are sort of higher level functions. These pre-existing onboard functions, such as fast start or inspection travel or peak curve, are heavily used and utilized, but it's the CiA 417 implementation, and so through that, basically the lift controller that is in charge of all of this and decides how these pre-existing functions are to be used. And then finally, at the sort of lowest level, or within the drive, is the internal drive motor control system, which is responsible in delivering the required current to the motor and generating the optimum torque to hold the lift car, move the lift car, accelerate and slow down the lift car, and ultimately hold it in place for the brakes to drop. Now, sort of going back the opposite way, so once all of this movement is happening, has happened, then the CiA 417 implementation, the module, if you will, returns any outgoing messages from the drive towards the controller back to the CANopen physical interface, and then the CANopen interface transmits these outgoing messages over the CAN bus back to the lift controller. So that's sort of how the control word, status word behavior operates, but I'll talk about that in a second. The way that so the reason why all of this is implemented in this way and the benefits of this topology is that each bit, the CANopen interface, the CiA 417 profile, the internal drive lift functions, and the internal drive motor control, they all exist as sort of separate layers within the drive. The benefit of that is that the CiA 417 implementation is discrete and can be updated to accept additional objects if and when they are added to the specification or as they are required by the lift controller or certain lift controller vendors. While as with the internal drive functions, these are implemented in the main drive firmware, and so that allows that the 417 implementation to remain lightweight while still being able to access all the complex features that exist within the drive. And also any core feature, any core updates that are applied to the drive features will be passed on. And so the 417 solution, the whole system, can benefit from any improvement that is made to either the internal drive lift functions or to the internal drive motor control system, all through a single update. Coming on to how the drive is controlled, and I basically highlighted this, that the main method, if you will, is always through the control word and then reported back through the status word. The drive can be fully controlled over the CANopen interface with the use of the control word. The only exception being is the safe torque off or STO input, which must be controlled via the drive's physical terminal. This is obviously for the safety of the system and the safety of the passengers. The safe torque off input basically operates as traditionally the physical motor contactors would have. So if the safe torque off input is disabled, then it is not possible to generate torque on the drive's out or current on the drive's output and generate torque in the motor. So it stops any movement from happening, or it can guarantee that no movement will happen. Before coming back to the control word and status word, just a bit on the state machines. So CiA 417 implements its own state machine and state monitoring, which is very much focused on transitions. So as it was said before, basically the lift controller initializes the system, and then basically from a starting point, drive goes from not ready to be switched on to sort of switch on disabled, to be ready to switch on, being switched on, operating, and then stopping from there, or if there's a fault detected, then the fault handling mechanism kicks in. So there's 16 transitions that are recognized basically between these states, and each of these transitions are monitored and logged, and ultimately it sort of monitors whether the system is not operating, ready to be operated, or actually operating. Now, in contrast to that, the drive itself being in control of the physical movements, if you will, of the system, implements its own state machine, and this is more state-based, if you will. So as you can see on this example travel curve, which shows what we call a directly floor operation, where there's no actual creep at the beginning or at the end of the profile. The drive normally starts in an idle state, so that is state 0. From there, it's waiting on the STO enable. So it's basically told that it's allowed to generate current on the outputs and control the motor. If there are physical motor contactors, then those get debounced in state 2. Motor torque is being cramped up. Brakes are released. The elevator car load measurement happens, and then starting from state 6, the actual travel profile starts, coming on to acceleration, reaching constant speed. Then after reaching a certain distance, deceleration. If there's creep in this profile, then the creep to floor and creep to stop is happening. The lift car is still held in place by the drive and by the motor. The motor brakes are applied in state 12. State 13, the motor torque is being ramped down. Gently, the car is basically lowered to hold against the brakes. And then finally, the motor contactors and the STO is opened, so the system is no longer energized. In the 417 state machine, as I mentioned, the transitions are mainly that's being tracked, while from the drive's internals perspective, it's again the states that are being monitored from state 0 up to state 14 and then back to 0. Now, what are the actual control modes and how travel happens? There's 2 distinct modes which can be used sort of one after another if decided by the lift controller, but once one mode of control or one mode of travel is initiated, it has to be followed through up to basically the idle point where another travel may be started with the other method. So with the profile position mode, which from our perspective, the drive's perspective, we refer to as direct to floor, this is a mode where the drive controls the travel profile, so not the lift controller. And this includes the deceleration and stopping of the motor and positioning accurately to the floor level. The prerequisite of using this mode is that the position feedback device is fitted and that the drive receives the same position information as the lift controller. So this is synchronized between the different devices. The controller sets the target position to the next floor in object 6420. The deceleration point is constantly refreshed during the travel and reported back to the controller via the control effort object 6406. And if there are no calls from the next floor, then the controller can update the target position, extending it to the next floor and basically creating a target position extension, so the travel carries on. Opposed to this is profile velocity mode, or what we call creep to floor. This is a more traditional method, if you want to call it that. So in this case, the lift controller controls the travel profile and the drive just executes. In this case, the lift controller provides the speed at which to travel, and the drive will begin to move the car at whatever speed is given until there's a speed update. When the system is in the correct state, so it's allowed to operate, the lift controller sets a non-zero value to target velocity in object 6430, and the drive starts the travel. After reaching the speed set point, so the target velocity, this is shown in the target reached bit by setting the target reached bit. To decelerate, the controller sets the speed set point to a creep speed, and then to finish the travel, the target velocity shall be set back to 0. To show these two modes in actual graphs, and that way it might be easier to see what's happening. So throughout all of this, one thing that's happening is that the CiA 417 state machine gets updated as it's relevant through the different stages of the travel, as well as I mentioned, the internal drive state machine gets updated. So the different commands are given from the lift controller to the 417 implementation. And basically, the travel starts. To use this, the controller must provide a target position and indicate that there's a new target position with the control word. Travel is happening, and in this window, before the deceleration, the remaining distance is constantly updated and reported back to the controller. The controller gives an update so that it extends the distance with a new distance value. And if the drive can accept this, it will acknowledge it with the status word. And then the drive will feed back the control effort to indicate to the lift controller where the deceleration will actually happen, so that the lift controller knows how much distance is left in which it can decide to command a new update and further extend this remaining distance. In velocity mode, so where it's all speed-based rather than position-based, and the lift controller is in charge of the profile. Again, the 417 state machine is implemented the same way. The drive's internal state machine, again, is ticking in the background the same way. But here, once again, everything is speed-based, and speed commands are given from the lift controller to the drive. The lift controller provides a speed, target speed basically, target velocity at which to travel. When this is provided in the correct state of the state machine, then the actual travel will begin, and the drive will output the requested speed until there's basically a new one. The new speed can actually be faster or slower than the previous one, and then ultimately the travel is finished when the speed is set back to 0. So all of this is actually profiled out and controlled by the controller. The drive just implements. Coming on to the key objects of basically everything I've described, the most important ones are 6400, the control word. So this object is how the lift controller communicates with the drive. The control word contains an assortment of commands to step the drive through the CiA 417 state machine, as well as additional information such as indicating there is a new target position, or the requested travel is an expression travel, which is a bit special. The status word, so 6401, this object is how the drive communicates with the lift controller. The status word relays information back to the lift controller, indicating which state of the CiA 417 state machine is currently active. Other indications such as target position reached, acknowledged new set point, 0 speed, position limit active are given back to the controller through the status word. 6403 is the mode of operation. So as I mentioned, This object is used by the lift controller to indicate to the drive which control mode is desired, whether it's profile position mode or profile velocity mode. This needs to be set prior to beginning a travel, as the drive will not accept a change in mode after a travel has begun. Once a travel has completed, this can be changed, but not throughout the actual travel. The control effort 6406. So the control effort is transmitted from the drive to the lift controller to provide information about deceleration distances. In profile position mode, the drive will feed back how far the lift car is away from the point where deceleration will begin. This allows the controller to send a new target position before the drive begins decelerating, allowing the lift car to remain at constant velocity and sort of having a smooth travel, a smooth ride for the passengers. So this is basically gives information to the controller what's the window in which new distance can still be given. In profile velocity mode, the drive will feed back the deceleration distance required from any current speed of the lift car to reach a standstill. So this basically gives information to the controller how far it will take for the lift car to come to a stop from any certain point, any certain speed. This is useful in profile velocity mode, as it indicates the appropriate time to begin decelerating. 6420, so target position. This object is used in conjunction with the new set point bit in the control word. The target position is set in the target position object. Then the new set point bit in the control word is set to indicate to the drive that there is a new target position. The drive evaluates if it can accept this new position. It can only accept the new position before it has begun decelerating. If the new target position is accepted by the drive, it will indicate this by the set point acknowledge bit in the status word. This process allows the lift controller to tell the drive to move one floor at a time, allowing for a call from a next floor to be serviced if required. If there are no calls to be serviced, the controller can keep extending the travel basically up to the top destination. Profile velocity 6423. So this object indicates to the drive what maximum velocity should be used when in profile position mode. This should be set to a maximum required value, even if that velocity cannot be reached in a specific travel in a requested distance. If a multiple floor travel is requested, the drive can accelerate up to the profile velocity and remaining at constant speed until deceleration is required. If a short travel is required, the drive will perform what we call a peak curve travel, where there is no constant speed. There is just acceleration and then immediately deceleration, which optimizes the travel curve. Target velocity 6430. This object indicates to the drive what speed and direction should be used when in profile velocity mode. So as profile velocity mode does not indicate the target position, the target velocity is used to work out which direction the drive should move the elevator car. So this is signed. The drive will accelerate to the required velocity and remain at this speed until a new target velocity is received. When a new target velocity is received, the drive will accelerate or decelerate to the new velocity, but come to a stop if a different direction is requested, indicated by the signed value. And coming to the end, a bit on additional features within 417. So inspection mode is commonly used. This is mainly when commissioning and setting up lift system. With inspection mode selected, the normal timing constraints within the drive are relaxed to prevent any nuisance error messages or trips. During inspection, the fast stop system of the drive is internally enabled, using a separate fast stop deceleration rate to decelerate the lift car to stop quickly, but still in a controlled manner. So for example, if there's an actual operator on top of the lift car and they are manually in control of the movement of the lift, they can use fast stop to have a sudden but still controlled stop of the lift, and therefore the operator at top of the car is still safe and are able to kind of nudge the lift car up and down in the shaft. Energy saving mode for UPS emergency supply. So basically to save energy while using an emergency supply, some comfort features of the drive are disabled. And to further aid energy saving, the drive's power limit control is turned on. So this limits the power taken from the power supply, aiming to slow down the depletion of that emergency power supply. We talked previously about keypad emulation. So many lift controllers support an emulated keypad. Normally, the way the drive works is that the drive internally only has its internal values, and it's actually the keypad that has the text strings, and that allows us to do translations as well. But for 417 to be able to implement the keypad emulation on the lift controller, the 417 implementation in the drive actually stores and transmits all the correct strings for each parameter and in multiple languages, such as German or English, which normally exists only as internal values within the drive. And as well as the strings to the parameters, the values are sent and then displayed to the user on the virtual keypad. And then the user can interact with these and change the values, and these then get sent back to the drive where it's interpreted once again as internal drive parameter values and set as such. And then coming on to the last bit, these are some of the features that are typically more vendor specific and kind of implemented differently in each drive, but I believe they are still crucial, and these are some of the functions that are commonly used or accessed even through the virtual keypad through the controller, because they make a massive difference in the overall electromechanical behavior of the lift system. So the stationary auto-tune is key, as it's basically how the drive acquires the correct tuning for each motor, and does so without actually rotating the motor. This is basically how the system, the drive motor system, gets set up. And often the lift controllers will have a mode that will permit an inspection travel without actually having any movement, sort of to support this auto-tuning process. So the lift controller can request an inspection travel without actual movement, and in the meantime, the drive can perform a stationary auto-tune on the motor and get the correct tuning values. Fast start. So for normal operation that is not using fast start, the actual travel is only started when the lift car doors are closed. With fast start, basically this sequence gets sped up so that the travel sequence can actually begin while the lift car doors are still open or in the process of closing, to reduce the start time and improve the flow of traffic within the building. For automatic load compensation, or what we call start locking and pre-torquing. So start locking is a feature intended to optimize the holding of the lift car when the brakes are released, and this can actually be done without a load cell or any form of physical load measurement. So basically, if set up correctly with pre-torquing and start locking, the drive can hold a lift car perfectly in position when the brakes are not holding, because they've been already released at the start of the travel. Start optimization is a feature that allows to overcome static friction and other starting problems in the system. Start optimization is using its own jerk and time and target speed, again, parameters which exist in the drive and which can be accessed by the lift controller or on the drive through the virtual keypad. Inertia compensation. This can be used to overcome the mechanical inertia of the lift system. It provides a dynamic torque feed-forward term based on the inertia of the lift system and the profile acceleration rate, basically reducing the demand on the speed loop control so it can compensate for in the in the acceleration calculations with the inertia. And then finally, brake control. If brake control is implemented on the drive directly rather than in the lift controller, then the drive is capable with its own onboard parameters to control the brakes and set mechanical brake delays. This can also be set up and accessed from the lift controller to the normal parameter accesses. And in this case, the drive also controls the brakes in the start and ending sequence of the travel. Thank you very much. That's all from me.